Lumentum makes lasers, fiber optics, and some other stuff. It has a wild history. During the peak of the telecom bubble, this company, with less than $2 billion in revenue, was worth more than GM and Ford combined. After it all came crashing down, the company languished in obscurity for over a decade. But now, thanks to the massive AI data center boom, it is so back. In today's video, the glorious rebirth of a fiber optic high flyer, and why. I want to thank Irrational, author of the Irrational Analysis newsletter, for inspiring me to do this video and working with me on the AI and laser section. Check out his newsletter in the description below. Act 1, Scene 1. We open at Bell Northern Research, or BNR, the research laboratory lab of the telecom giant Nortel in the 1970s. Canadians Joseph Strauss, Gary Duck, Philip Garrell-Jones, and Bill Sinclair are part of a team working on components for the first optical fiber technologies. Their efforts relate to reducing noise and increasing data capacity for carrying multiple video streams. One technology they focused on was dense wavelength division multiplexing, or DWDM. This lets a type of optic fiber called single-mode fiber carry multiple signals simultaneously by encoding them in different light wavelengths. Such signals can be switched, routed, and separated without fear of interference. Fiber optics are a wondrous technology, but also have an infamous reputation as a destroyer of capital. Prior to the 1990s, Nortel's fiber optic business lost money for 10 years straight. So Nortel, somewhat understandably, didn't want to make these fiber optic components in-house. When that became clear, Strauss, Duck, Garrell-Jones, and Sinclair left in 1981 to start JDS Optical. JDS Optical produced passive fiber optic network components, meaning those that control light without using any power. Optical couplers, splitters, filters, and isolators. In 1990, they struck a distribution and technology sharing deal with the Japanese giant Furukawa Electric. Furukawa bought half of the company for about $9 million. As part of the deal, JDS Optical changed their name to JDS Vitel, Vitel being a Furukawa brand. Over the next few years, the company produced optical switches, couplers, and lasers, essential items for optical fiber networks. Overall, people knew them as a quiet, low-key company that kept their heads down. In this manner, the company emulated its co-founder and second CEO, Joseph Strauss, a private individual who immigrated to Canada from Czechoslovakia prior to the 1968 Soviet invasion. He's known around Ottawa for wearing a black wool beret. Demand for fiber optic components grew steadily, but linearly, throughout the 1980s. And when you're carrying just telephone calls, faxes, and even emails, like with the early internet, capacity demand expanded at just about 8% a year, nothing to write home about. Then in the early 1990s, we had the rise of the World Wide Web, and suddenly telecoms were in a race to build out fiber optic networks for all the internet's revolutionary functions: streaming video and audio, e-commerce, faxes, what have you. CEO Joseph Strauss explained the core trend in a 1998 interview. The entire telecommunications industry is growing like a fast-spinning vortex, driven by the need for more bandwidth at lower costs and greater flexibility. JDS Vitel found itself in a fortuitous position. They were the leading supplier of DWDM equipment, which let telecoms raise the data capacity of their networks without needing to tear out and replace the fiber, which is prohibitively expensive. JDS's revenues grew at 65% annual growth rate between 1994 and 1998. In March 1996, they went public, raising about $93.7 million. The stock quickly surged 52% to about $18.25 in August, a few months later. Then, in January 1999, JDS Vitel announced that it would merge with another California-based rocket ship called Uniphase Corporation in a stock swap transaction worth about $6 billion. Uniphase is a classic Silicon Valley entrepreneur story. The company was founded by an engineer named Dale Crane from the laser maker Spectra Physics. Spectra Physics is one of the OG laser companies. They were founded a year after the laser's invention and helped commercialize it. One of their products was a small helium neon gas laser for scanning supermarket barcodes. It helped speed up the checkout process but had to be integrated into the counter. Crane felt that it was possible to build a similar laser but smaller, small enough to put into a handheld. His bosses were not interested in that. So in 1979, Crane left to start Uniphase in his garage with $300,000 of savings. After a year, he finished his laser and sold tens of thousands of laser units to manufacturers. His vision of a handheld laser-based grocery store scanner produced by Symbol Technology became reality. Uniphase revenues grew rapidly, allowing Crane to build more complicated laser products, moving up wavelengths from helium neon red lasers to argon blue and even CO2 lasers. In 1992, Uniphase's board appointed a bold software executive named Kevin Kalkhoven as its CEO. Kalkhoven's mandate was to accelerate the company's plodding growth and IPO so that investors can get a financial return on these random laser experiments. Kalkhoven first led an entry into the semiconductor industry, producing a defect scanning inspection tool called the UltraPoint. It scans a blue argon laser across the silicon wafer to find defects as small as 0.1 microns in diameter. UltraPoint was a fairly successful business that eventually boosted Uniphase towards their 1993 IPO, which valued them at about $30 million. Then in 1994, Kalkhoven read a magazine article profiling how MCI, the Telecom, used an amplified laser beam to send data from Chicago to Sacramento. The beam was sent via optical fiber with relatively little loss. No need for electrical equipment to regenerate the signal through copper wires. Kalkhoven immediately became a true believer in the technology and proposed to reorient the company to this new space. At the time, this was an unpopular move. Kalkhoven personally had no experience in telecommunications, and Uniphase had no experience in the semiconductor lasers used for telecom. Their expertise was in gas lasers, as I mentioned earlier. So more than a few people were skeptical. Paul Crane, for his part, thought the man was crazy, sold off all his shares, and disembarked to Nevada to raise a family. But Kalkhoven pushed forward. In 1995, he paid $8 million to buy defense contractor United Technologies' Photonics Division. UT was then going through the early 1990s post-Soviet defense bust and needed to slim down. The purchase was as risky as can be. Kalkhoven was betting the company, but it gave Uniphase their first critical fiber optics component, a reliable, low-power lithium niobate modulator that could modify a laser beam at gigahertz speeds to encode data signals. Uniphase then went on to build up the company's offerings with a raft of acquisitions, including IBM's laser diode division in Switzerland in 1997. In 1998, they swallowed up Philips's optoelectronics group in a complex stock swap. The transaction helped complete Uniphase's lineup of semiconductor lasers from the fiber optic industry. Previously, they only offered 980 nanometer lasers. Philips provided two others, 1310 nanometers and 1550 nanometers. Then in 1998, Kalkhoven got a call from JDS's Strauss, asking whether he might be interested in doing something together. So the two CEOs went on a hike in the Colorado Rockies, as rich CEOs do, and hashed out how a combination might look like. The deal was finalized in September 1998 near Lake Tahoe, and as I said earlier, was announced in January 1999. The combined company, called JDS Uniphase or JDSU, began life in July 1999. Kalkhoven would serve as CEO and co-chairman. Joseph Strauss became COO and the other co-chairman. The latter celebrated by giving away thousands of his trademark black beret. The company, JDSU, had sales of about $587 million and profits of $124 million. More importantly, the combination brought together JDS's strengths in passive fiber optic components and Uniphase's strengths in active components. The company can now serve as a one-stop shop for buyers like Lucent and Nortel, who use those components to produce equipment to fulfill the seemingly insatiable demands of telecoms like Quest, Global Crossing, Level 3, and 360 networks. Investors loved the merger. The stock soared 12% when it was announced, and they kept loving it throughout the year. JDS Uniphase's stock went from a split-adjusted $17.25 per share in January 1999 to $161.35 by December, and it just kept going. Using its ballooning stock price, JDSU went on one of the telecom bubble's wildest acquisition sprees, which is saying something considering that this was the peak of the telecom bubble. Companies like Corning, Sarent, and Lucent were all shelling out billions to buy startups at inflated valuations. But JDSU, you should see them feast. They were like a mantis. In the second half of 1999 alone, JDSU bought 6 companies, including a $2.8 billion all-stock deal with Optical Coating Laboratory, a maker of optical thin film coatings. Then, in January 2000, they announced they would purchase a rival fiber optic components and modules maker called E-Tech Dynamics for about $15 billion in stock. Despite the high price, analysts hailed the deal because it gave JDSU a dominant 2/3 share of the fiber optics market. In other words, it now made them the Intel of fiber optics. Yes, they are like Intel now. In March 2000, the Nasdaq hit an intraday high of 5,132. JDSU's buoyant stock hit an all-time high of $293, rising 82% in just 3 months from January. It had risen a ridiculous 220 times from what it was 4 years prior. March marks the beginning of the end for these twin bubbles in the late 1990s. From there, the Nasdaq index began to descend as various gimmicky dot-com stocks imploded. Despite the ongoing dot-com meltdown, the fiber optics stocks stayed hot for a while. One infamous IPO in late July 2000 valued a fiber optics component startup called Corvus at $11 billion, despite them not having a single shipping product. Founder David Huber's stake alone was worth $1.86 billion. Cal Coven decided then to step down from JDSU. He would later get into racing cars. Strauss took over as the company's CEO and swiftly led the company to its biggest buy yet. In mid-July 2000, JDSU's market cap was $110 billion, more than GM and Ford combined. Their trailing 12-month revenues were just $1.4 billion. And the company showed a net loss of $170 million, though most of that was from amortizing the company's goodwill from its purchases. Strauss then negotiated to buy rival optics fiber components maker SDL for a staggering $41 billion in stock, or about $76 billion today. It was the largest non-telecom technology company acquisition up until then. This particular transaction was wild. SDL's trailing 12-month revenues were only $187 million. Profits just about $25 million. Paying $41 billion for so little, even if it was all paid in stock, boggled the mind. Business Week ran an article with the title, "Is JDS Uniphase Bonkers?" and asked if management had lost their minds. If your stock is overvalued, which it was, you use it to buy undervalued assets. Don't use it to buy other overvalued companies. In late July 2000, JDSU's split-adjusted stock price had retraced a bit from the peak of an adjusted $293, but was still at a pretty good $135. Unfortunately, worse things were yet to come. Telecom capex continued in the third quarter of 2000, but the engine was sputtering. Lucent and Nortel had controversially lent billions to telecoms to buy their equipment. When those small companies collapsed due to the fiber overbuild, that came back to bite them. The pain took no time to filter down to JDS Uniphase. By late September 2000, the stock had fallen to $95. By December, it had spiraled down to just $41, and now the alarm bells were seriously ringing. In January 2001, JDSU laid off 700 contract workers in Ottawa. A month later, Nortel abruptly cut their forecasts. So then a week later, in February 28th, JDSU announced a 10% cut to their workforce, 3,000 layoffs. The stock price fell to $29. A company spokesman said, "We still feel very strongly about the need and demand for bandwidth. We still think it's there." Unfortunately, he was wrong. Demand for fiber optic components was vanishing faster than an ice cube in the Sahara. A week later, in March, JDS admitted that they will miss their third and fourth quarter earnings forecasts. Internally, it was chaos down and up the ranks. Employees were hearing about job cuts on the radio before the managers can be informed. Considering that the rest of the telecom industry was imploding too, Nortel alone would cut an astonishing 50,000 jobs in just the year 2001, it caused a lot of anxiety. In late April 2001, JDSU announced that they would cut another 5,000 jobs, half of which would be in Canada, where JDSU had many core research and engineering staff. The stock continued its march to Hades by falling 14% to $20. In July 2001, they declared a $50 billion loss for the 2001 fiscal year and another 7,000 job cuts, a third round on top of what had already been announced. At their peak, JDSU had 29,000 employees globally. 16,000 of those were chopped in 1 year. By late August 2001, the stock price was $7. A year later, in August 2002, it reached $2. Even as the stock stumbled, analysts declared their faith in the seemingly quote-unquote stratospheric future of communications and the internet. Meanwhile, management raked in millions selling their shares. I know that some today argue that there are good and bad bubbles, pointing to the telecom bubble as one of the good ones because it created internet capacity. Considering the social and economic annihilation of entire communities in Canada and the United States that the bubble's burst left behind, I am skeptical. For the next few years, JDSU continued to show losses. A year after their first immolation, they announced another $8.7 billion loss for the fiscal year 2002, mostly due to billions in write-downs from the 17 or so acquisitions made during its wild and woolly years. Fortunately, the company did almost all of its purchases using stock rather than cash. They had no debt and were cash flow positive. So ultimately, after cutting enough jobs, the company managed to limp through these hard times. In August 2003, Strauss retired. His legacy for Canada is mixed. He helped create thousands of high-paying engineering jobs in his adopted home of Ottawa, but under his purview, JDSU hyped the fiber bubble and then annihilated billions in people's life savings and cut 95% of the jobs in said adopted hometown. The fiber overhang meant that JDSU can no longer rely on new fiber component sales, so they pivoted to providing testing and maintenance services for those customers with the 2005 purchase of Acterna. By now, revenue had shriveled to just $166 million. The stock plopped to $1.50. But this pivot was the right move, and over the next decade, the company quietly expanded its portfolio of stable but boring service businesses. Stuff like fiber optics cleaning and network testing services. The latter became especially attractive as cloud computing became more prevalent. They also seem to have spent some money to get into the business of anti-counterfeit stuff like those special color-shifting optical inks that you can see on currencies. Pretty cool. In September 11, 2014, JDSU announced that they were going to spin off their optical components and commercial lasers businesses. The old JDSU entity, later to be renamed to Viavi Solutions, retained the various network service, installation, and test businesses that helped the company survive the past 10-plus years. Management explained the move as giving investors more clarity. JDSU had been 3 businesses under one umbrella, and it was clear on the investor call that management valued one of those 3 less than the other 2. The optical hardware business was strong, but faced heavier competitive pressures. And since it was also a manufacturing business with fabs and capital requirements for them and all that, its profit margins were rougher. The various network and service enablement businesses, on the other hand, are more software-centric, with 60% gross margins. Management also felt that great opportunities laid ahead for that, thanks to the ongoing rise of the cloud and data center. Thus, the laser business was being sent off on a raft to fend for itself, fortunately without any debt. It is most telling that the old JDSU management opted to stay with Viavi. In February 2015, it was announced that the spin-off would be named Lumentum. Lumentum's core business involved lasers for fiber optics, but for a long time that wasn't growing much. So the company experienced its next big expansion thanks to the rise of 3D sensing. These rely on small near-infrared dots generated by an array of compact little lasers called VCSELs. The technology first gained some prominence when Microsoft used it to produce the Xbox Kinect, a device that lets you use gestures to game. I never used it, but I heard it was fun. JDSU talked it a lot in 2011. But the real turning point occurred when these 3D sensing tools were adapted to do facial recognition on the mobile phone. These first broke through with Apple's iPhone X, which hit the market in November 2017. Lumentum supplied all the VCSELs for those devices, though the Cupertino Fruit Company quickly diversified to a second supplier by investing in Finisar, now part of another optics company called Coherent. The company continues to work on VCSELs for LiDAR production, extolling their potential benefit for applications like self-driving. But 3D sensing is not behind Lumentum's rapid growth as of late. AI is that reason, of course, but what are they doing that is so special? I am no expert, so as I mentioned earlier, I invited the anonymous author of the Irrational Analysis newsletter to help. What follows is his analysis, though I made some edits so I can narrate it. Lumentum's value in the AI boom is tied to a shortage of high quality, as in low noise, high density photons. Let's start with understanding density. Co-packaged optical or CPO systems like those shown by NVIDIA and Broadcom want ultra-high power continuous wave lasers. For the lasers inside traditional optical transceivers, it was historically sufficient for them to have an optical power of around 20 milliwatts. Co-packaged optics, however, require much higher optical output power per laser, typically in the range of 200 to 400 milliwatts. This is because CPO solutions use external pluggable light sources called ELSFP modules rather than have them directly integrated into the system. Disaggregating the lasers from the rest of the system makes sense because these lasers are typically the most unreliable and failure-prone element of an optical system. They're also very temperature sensitive, necessitating precise active cooling using thermoelectric coolers. So moving the lasers to a dedicated pluggable module, the same form factor as a transceiver, greatly helps reliability. However, there is a cost drawback with doing it this way, particularly involving the fibers. The fibers connecting a continuous wave laser and the optical engines must be of a particular type. Polarization maintaining PM fibers. What are those? Imagine a pair of sunglasses. Sunglasses reduce glare by filtering out light that is in the wrong quote-unquote orientation, aka polarization. Polarization maintaining fiber is designed so that the light coming in stays on the same axis. Bad polarization leads to massive optical losses, so PM fibers intentionally build in internal stress elements to force the glass core into a desired shape. This helps ensure that the most light possible makes it from the laser to the silicon photonics optical engine. It also makes PM fibers expensive, so people want to minimize how much they use it for each system. Attaching those PM fibers is also expensive and quite painful. Typically, the attachment process means aligning the fiber, as well as a micro lens, to a target surface, usually an indium phosphide laser or a silicon photonics photonic integrated circuit. Once aligned, we use epoxy to hold it all together. This is not easy. So, More PM fiber attachments mean more cost plus additional potential points of failure. So using 4 100 milliwatt lasers is not the same as one 400 milliwatt laser. Economic and reliability requirements place significant pressure upon a laser vendor like Lumentum to deliver as much power as possible within a single laser diode. Lumentum's ultra-high power lasers deliver up to 24 dBm optical output per wavelength at 50 degrees Celsius. That 24 dBm converts to about 250 milliwatts of output power. This is the power that makes it onto the fiber. Every coupling interface induces optical loss, thus a non-trivial amount of light is lost between the indium phosphide laser and the fiber within the ELS FP module. In general, the ultra-high power class of lasers is around 350 to 400 milliwatts optical output power at facet, meaning before any coupling loss. This corresponds to 25.5 to 26 dBm. As of this writing, only 3 companies claim to have ultra-high power class of continuous wave lasers. Those are Lumentum, Coherent, and Applied Optoelectronics. Broadcom has an internal laser division that presumably has a solution, but they have not advertised their precise optical power specs. But power is not the only story. The quality of the photons is also critical for modern CPO systems, particularly those using ring modulators. 2 key specs determine how quote-unquote noisy a laser is: line width and relative intensity noise, or RIN. Let us go through those one by one. Lasers don't stay at one exact frequency. They actually jitter across the optical spectrum. Line width is the width of that jitter, thus telling you the laser's sharpness. The sharper, the better. It is typically measured at the 3 dB full width half magnitude point. So how wide the plot is when it is at 50% of peak power. Many factors can influence a laser's line width, including thermal noise, power supply noise, or even optical reflections back into the laser itself. But the most important factor is the quality of the laser's design, as well as the manufacturing process that made it. Achieving a line width of 1 MHz or less is highly desired by the co-packaged optics boom, fueled by AI requirements. It is extremely difficult to hit this number at high power because of how DFB, distributed feedback lasers, work. Unlike normal lasers, DFB lasers use many tiny mirrors called gratings that bounce light back and forth in a feedback loop. This loop raises the laser's power while also sharpening/concentrating light. The issue at higher power levels is that the DFB laser becomes much more sensitive to very small imperfections in the grating's design or fabrication. The effects of any imperfections amplify, creating a much noisier laser. In addition to line width, the other measure of noisiness is RIN, or relative intensity noise. Is it RIN? I like to call it RIN. If line width is noise going side to side, then RIN is amplitude noise. Laser power intensity fluctuates up and down randomly over time. RIN measures that intensity noise. RIN measurements are also in frequency domain, but the final number is an average between 2 values. The lower bound is defined by the optical system's tolerance to low frequency noise and is typically around 0.1 to 10 MHz, while the upper bound is often determined by the Nyquist frequency of the communication system. So, a system designed for 112 gigabits per second Ethernet might measure RIN from 10 MHz to 28.5 GHz. Again, many factors contribute to laser RIN, particularly the quality of the electrical driver and thermal control. Yet the most important factor, again, is the quality of the laser design and fabrication itself. Lumentum is the only independent laser vendor who can achieve these 2 key low noise aspects, line width and RIN, while also achieving high power. This makes it a key player in the AI-driven co-packaged optical revolution. As of this writing, Lumentum, the company, has a market cap of around $50 billion. Quite volatile, so be careful about that number. And it was just announced, as of this writing, that Lumentum and NVIDIA are collaborating to enable next-generation AI silicon photonic systems, along with building new manufacturing capacity. I don't know where the AI data center boom goes from here, but I am fascinated to see how it has empowered entire technology fields or given them new life. Fiber optics is back again after 20 plus years in the gulag. Let's go. All right, everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the Patreon, and thanks again to Irrational for spending time with me on this. All right, everyone, have a good night.